Let's remember that the solution to a system of linear equations is a pair of numbers. That makes our equation a true numerical equality. But we are discussing the graphical solution of systems of equations. I would like to draw your attention to the fact that solving a system of equations means finding all pairs of numbers that constitute the solution or proving that no such pairs exist. When we solve a system of equations graphically, we find the intersection point of two function graphs, and the coordinates of this point are the solution. Yet, there are cases where no solutions exist. What happens in this case? We will visually see why there are no solutions for the system of equations. To illustrate this, we will solve our system of equations. We need to graph each function as per the rules. For this, we will write the first equation y, x equals -3. According to the rules, we express the variable y in terms of x, resulting in y equals -3 plus 2x. To graph this, we need to select 2 points. Why 2 points? Of course, it is possible to select many points, but for linear equations, 2 points suffice. We will note that the value of x equals 0. If x is equal to 0, then y will equal -3. If we substitute 0 for the variable x, we get -3 plus 2 times 0, which is -3. Now, the next value we will use for x is 1. By substituting 1, we find that -3 plus 2 times 1 results in y will equal -1. Let me remind you that you can use any numbers in place of x, and you will still obtain the graph of this function. Let's mark these points with coordinates 0 and -3 on the coordinate plane. This point here. The second point is at 1, 1. We begin at the point 0, 0 on the x-axis and 1 on the y-axis. Thus, we arrive at the point 1, 1. According to the rules, to draw the graph of this function, we must draw a line through these 2 points. I will draw a straight line through these points. This is the graph of the function y equals -3 plus 2x. Now let's look at the next equation, 2x plus y upon 6. In this case, we will also express the variable y equals 6 plus 2x. Then, we need just 2 points, and we will calculate y. For x, I will set the value to 0. You might have seen that I substitute 0 for x every time. It's convenient to compute this value, so y will be equal to 6. Now, instead of x, I will substitute a value equal to -2. Then, if x equals -2, 6 plus 2 multiplied by -2 equals 6 minus 4. As a result, y will equal 2. Let's plot the graph of this function. The first point is 0, with coordinates 0, 6. Here is the point. The second point has coordinates -2 and 2. -2, 2 units to the left, and 2 up on the y-axis. Thus, we have 2 points again. Now we will draw a line that passes through these points. What did we see? These lines are actually parallel. And if the lines are parallel, then they have no common points. They will never intersect. Of course, you might ask, what if we extend the line further and the graph of the first line and the graph of the second line, we also extend further, either up or down, maybe they will intersect. I maintain that these function graphs will never cross. Hence, this system of equations has no solutions. No solutions exist. You will not find the point that is the intersection of these lines. Yet, you might wonder, what if I continue these lines? Maybe they will intersect somewhere. But in this case, I can tell you for sure that these lines are parallel. What to focus on? In the equations? To the coefficients associated with the variable x. If these coefficients for the variable x are equal, then the graphs of these functions will be parallel. However, we also need to take into account the coefficients for y. As you can see, in the first equation, the coefficients for y are equal to 1. The second equation also has y's coefficient as 1. If the coefficients for both variables are equal, the graphs of these functions will be parallel. Next time we'll solve another system, but differently. That's all for today. Goodbye.